Yeah, my name's Keduse Worku. I'm a rising senior at Yale University. In the summer through SNSP, I worked with Joe Dunkley's team at Princeton, including Audrey, Zach, and Emily. And the primary person I interacted with on a daily basis was Audrey. So in general, it was a cosmology project, and we were searching for this correlation, the ISW-TSC cross correlation. I'll explain the individual portions of that in the coming slides. I won't do too much on background. You guys have done a great job in covering a lot of this already. But yeah, the CMB is the relics of the last scattering when light was first free to travel across the universe, so dispersed in all directions. It's redshifted now to the microwave range, and it kind of defines the edge of the observable universe, and we can get a whole lot of great information from it, early universe-wise and modern. And so that's what we were focused on. The data that we used was Planck maps. So the latest mission to characterize full sky observations of the CMB was the Planck satellites. And so the way that they worked was it's a series of maps that looks at different frequency ranges in CMB. And they made a whole lot of different kinds of maps that are through different methodologies, but the base of it was these different maps with different frequencies. And so we looked at two late time contributions to the CMB. Like I said, ISW-TSC. The first one being the ISW, so the integrated Sachs-Wolf effect. So yeah, this can be thought of as an imprint of dark energy onto the CMB. The base idea of it is, once again, the CMB is in the background of everything. So when that photon gets to us, if it goes through a large potential well, a large gravitational potential well, it travels into the well and it gains energy doing so, and then travels through it, and then it leaves the well, and it loses the energy that it gained generally. But with the ISW, we're looking at potential wells that are large enough such that the photon feels the expansion of space due to dark energy, and so the well actually gets shallower, and so these photons, individual photons, will travel a greater distance falling into the well than leaving it, and so they gain energy through this expansion. So it's blue shifted in a sense. For this to happen, the photon actually has to feel the expansion of space. So it happens at the largest scales of the CMB, the largest possible structures. So really large gravitational wells. And the next effect, Morgan touched on this a lot, which is wonderful. She really explained it well. It's a TSE effect, thermal. Well, mine specifically is the thermal. There are a few Simons-NSBP effects. And so this is once again a frequency-dependent effect. And this is with the intra-cluster medium. So cosmic microwave background, the background of everything. As that photon goes through a galaxy cluster, within galaxy clusters, there's this intra-cluster medium, which is this slew of protons and electrons, very energetic, it's just this plasma. And the photons will interact with the free electrons, and they'll get reverse Compton scattered. They always gain energy, it's always blue shifted, but depending on the frequency of the Planck map you're looking at, it can either show up as an increase or a decrease in the antenna temperature. This is really well characterized by this expression up here, in which Y encodes all of the information about the galaxy cluster in terms of the distribution of electrons, the important information anyway, while G characterizes the frequency dependence, which is once again a known function. And through these, we're using Planck data, Planck maps, and we use two different kinds of maps to characterize these two different effects. First of which is the SMICA map. So this is made with the Planck maps. It's linear combinations of those initial Planck maps, and this is based off of the black body of the CMB. The CMB acts as a black body. And so it keeps the data that aligns very well with it and throws away the data that doesn't quite as much. Clean for foregrounds, and you'll also see a snippet of something over there, and then it comes back there. That's actually the plane of the galaxy. So that's a very dusty location that we're not interested in, so we blocked it out with the mask. It's great. It is a mask that came with Spica. But we also blocked out some other portions, here, there. So those are point sources that are very bright and once again noisy. So the combination of the SMICA map and the point source map helped us to clean this well. So with this, with the SMICA mask rather, this is meant to generally capture the ISW effect. And the next map that we use, the Y map, focuses on the Soinev-Zeldovich effect. this is, optimized for that in terms of, once again, a linear combination of the Planck maps. We use the same masks, the galaxy mask and the point source mask. And with these two maps, we created some spectra. People have done a good job of explaining spectra before, so once again, I won't belabor it too much, but spectra in general demonstrate variance as a function of scale. Here on the x-axis, you see L's, very large L's. You represent small angular scales. So the scales of galaxies, for instance, this is cosmological scales. And small L's represent very large angular scales. You can see the very characteristic black body in the SMECA map because it's based off of the black body of the CMB, while with the Y map is optimized for the TSC effect, so it looks a little bit different. There are a few things to point out here. One of them is that in order to make a power spectra, you first need to take a cross correlation. And that's looking at two maps, seeing what they have in common, keeping that information, and then discarding the information that's independent for both of them. So initially we just did auto spectra. So that's when you do a cross correlation, but with the same map on both sides. You're comparing a map with itself, essentially. But you can do it two ways. You can do with a full mission or half mission. So we initially did the full mission. It's the the curve in orange on both sides. But the split mission is when you take the first and second half of the mission, still the same data, and then cross correlate them together. What you can have then is the same underlying signal, but you remove the independent noise. And so you see a great reduction in that. Reduction in noise in both of these, but you see a much greater reduction in the Y map along a greater range of L's. This is maxing out at 2K for L, and it's larger for the other spectra you've seen. But this is the range that we're interested in, actually a smaller range, but this is a nice picture. So this was also corrected for the fact that we're blocking out so much of the galaxy here and the point sources with this package the master. And we also corrected for the fact that this instrument beam has an effect. And so looking at the ultimate goal of this project, finding this cross correlation between the TSC and the ISW effects, we want to cross correlate these two maps together, the SMECA and the Y map. And so there's some great theory papers that lay out what we should expect. Once again, the reason why we expect a correlation to exist in the first place is with the TSC effect, the thermal effect. It happens in galaxy clusters, the intercluster medium, and the ISW effect happens in large potential wells. Well, we have galaxy clusters that sit in large potential wells, so they're in the same physical location, a lot of the same physical processes, so we expect them to be correlated. These papers lay it out very well. And the purple curve up here is the full CMB. That's very similar to SMECA up here, but these are log scales, so it looks quite different. But the red curve is what the theory prediction for the ISW TSC cross correlation. It's much smaller. Once again, these are log scales than the actual CMB signal. And to give a little bit more additional motivation, this is also previously unmeasured cross correlation. There's been cross correlations with the ISW effect, the dark energy, gravitational well effect, and galaxy clusters. And I mean, galaxy cluster catalogs like Sloan with YMAP or Planck with general cluster catalogs, but not quite with this correlation. And so this is our first go at it, and it is not what we expected. It's negative for one, and that implies an anti-correlation. So we did a little bit more investigating. Here we're actually not using the initial mask that I talked about, the SMECA plus the point source. We're always using the point source map in addition to other ones, or the point source mask rather. But we're also using a 40% galaxy mask, so this blocks out a little bit more of the galaxy. And so in this next plot, I show all of the different masks that we use to try to dig a little bit deeper at the problem, see, the question rather, see what's going on here. So we see a few different things. I'll point them out one by one. One is that you see a great reduction in this anti-correlation, this negative value, when you go from the SMECA mask to the other masks. And blue down here, and then all the other ones. So this is somewhat of a good thing, or very much a good thing rather. If we go back to this theory curve, this is in units of Kelvin, while we're in microkelvin, but the actual theory curve would be very, very close to the zero line, so much smaller in terms of scales. And so getting close to that curve is what we want. So yeah, it ended up being a good thing that we masked more and more of the galaxy. We saw, more and more approximately closer curves to that. Um, our initial guess was there's some kind of contamination going on. We don't know what it is, but there's some kind of contamination. There were a few candidates. One of them is the CIB, which is the cosmic infrared background. So in the same ways that there's the CMB, there's the CIB. So galaxies in general have a ton of dust. This dust is heated up in a lot of ways, and it emits light in the infrared range. And so this happens throughout the entire night sky. So it's the CIB. That wasn't quite the case because we're blocking out more and more of the galaxy. So if you're reducing the signal, if you're reducing the data, but you expect just increase in error bars, but not any movement in terms of the y direction. We're seeing movement in the y direction, and so that's not the leading contribution in terms of contamination. But we are seeing a reduction when we mask out more of the galaxy. So the biggest implication is that it's likely our own galaxy that's being contaminated in both of these masks. Once again, it can't just be one of them because when we take the cross correlation, you're eliminating the things that are independent to both of them. You're only keeping the things that they have in common. So both of these maps rather, must have had some kind of contamination. Once again, we're assuming galaxy. But the question is, why is it negative? Why is there an anti-correlation? And this, what we currently believe anyway, is that this is due to the way that these maps are created. The Y map prioritizes the TSC effect, while the SMICA map prioritizes the black body. And so the same foreground sources can show up as negative on the Y map, but positive on the SMICA map. It's the same sources, but just due to the methodology, it can have different signs. And so they are in fact truly correlated because they're the same foreground sources, but they're still just negative signs. There's nothing that truly physically different going on. And so we have a few next steps that we can do with regards to this. The first is changing the map that we use. SMICA is, once again, somewhat of a blind method. It takes the data that's very similar to the black body, rejects the data that's not. The commander map would be a little bit better because it characterizes a lot of the foreground processes from CO line to synchrotron radiation. A whole lot of different processes. It better characterizes this, so it would have less contamination of the galaxy. Another step would be using the ACT Galaxy Cluster Catalog to create our own mask in addition to the ones that we're using. So by eliminating the closest galaxy clusters, we can actually really reduce, or we can really increase the signal to noise ratio, because the ISW effect is most prominent in clusters that have a high redshift. That's the ultimate goal of this. And so the closest clusters both have the greatest contamination and are least impacted by ISW effect. So these would be some of the next steps to hopefully get closer to that theory curve, figure out why we're not. And many thank yous. Thank you to the program. Thank you to Casey. Thank you to Abby. You guys have done a tremendous job. Thank you for my team. I really appreciated all the coding help that they gave. I didn't know what I was doing for a long time. I still don't, but they just answered so many questions that I had. It's really a lot of multi-hour Blackboard, what's going on, a lot of coding questions. I really loved working with this team and the culture there. Thank you for everyone in the program. It was just a wonderful summer, and I really appreciated it. It's been a good time.
Anybody have questions for Keduse? Morgan?
I think it's a yes and no. So I have I have one more semester, and I'll be finishing out classes, but I'm also going to be applying to grad schools, and that's going to be taking a significant amount of time. But I'm also really invested. I really love this project. I love a lot of these topics, and I think I want to continue it in general in the future. And with such concrete next steps, I'm like, I want to do it. I want to see what's actually going to happen. So it's a jumble of feelings.
I have a question. You mentioned that this correlation between ISW had.
Would you mind using your seat, Mike?
I would not mind. You mentioned that the ISW has been correlated with clusters before, but never with the TSZ. So my question is, what do you get out of, if you can measure this correlation, does it tell us something new, physically new about our universe?
I don't feel confident enough to give you a good answer. I think I'll just say that one of the interesting things about the ISW effect is that it is an independent probe of dark energy, rather than just like full-on cosmological constants using them. And so finding both the ISW and the TSE cross-correlation within clusters, I think can give you better constraints on the ISW effect as well. And so in that way, it's a better probe of constraining the dark energy cosmological constants.